we'll see that they can solve the text indexing problem, but they can also solve several other interesting string problems, including this longest common substring problem that Don Knuth conjectured not to be solvable in linear time, but suffix trees actually make this possible. So here's again a suffix tree example. As I said before, you should really think about suffix trees as this thing on the right. So suppose there were all the labels of the edges spelled out as strings like this. That is just to make it easier to think about it. It's actually represented in the computer like this, and this will be important to make sure that the space works out. But for working with them, we will just pretend that this is what we have, and we can then, in a second step, we can think about how to simulate anything that these labels can do in the way they're actually stored in the tree. A little additional technical assumption is that we'll also assume each internal node has a pointer to the leftmost leaf in its subtree. This is something that you can easily, once the tree is constructed, you can easily walk through the entire tree once and make sure that this is true. But we'll assume that, for example, the root points to this one, and this one points to this one. So it's just an additional field in each node. And well, here in this example, it looks like it's always just a child of that node, but that is not in general true. You can have cases if you suppose that these two branches were swapped the other way around. Then you would jump down to the 7, which is not a child but a grandchild, and in general it could be arbitrarily deep in the tree. All right. So that's just a technical assumption. It's easy to maintain and easy to make sure that this is true, but this will make the applications easier to discuss. Okay, time for you to get active. Before I want to talk about text indexing in more detail, here's a question for you. I'll try to leave this here so that you can see the tree. You're given a suffix tree here on the left, and the question is, how much does this tell you about whether a pattern occurs in the text here? So take all the answers that are correct for this specific example. So the text that gives this suffix tree and this given pattern. I'll give you a minute to work on it and maybe show the big suffix tree instead. It's the same. Big surprise. I'd like to see a few more answers before we move on. Okay, I see 15 people have voted. Maybe we can get to something like 20, 25. It was 30 in the first poll. So the magic number should be our 25, right? Maybe what I should have added is, I don't know. I put in another option. If you feel like you have no idea what I'm asking, then just say don't know. That's also interesting to see if I lost you. Okay, we're getting close to 25. So 2 more, come on, we can do this. And it's a lot of answers, so I'll have to scroll around. One more. Yeah, there we go. Okay. I think I'll just show these and we'll discuss them on the slides because it's a little nicer to have the tree alongside it. Yeah, so probably should lock this now, otherwise you keep changing your mind. It doesn't tell you nothing. That would be a bit useless. It does tell you that P occurs in T in this case. And let's see if I can. Nah, no way. Okay, I'll come back to it. Well, that's the opposite, but it also tells you how often the pattern occurs in T, and it tells you where exactly. And for that, I'll probably want to go back to the bigger picture and make it real big. So we're looking at this tree, and we're trying to find the occurrences of Anna. Oh, this is not an A. Oh, I see. I'm drawing with a dash pen. So we're trying to find Anna. So what we have to do is we start in the root, and now we find the edge with an A. We follow it, then follow the edge with an N, and then the edge with an A. That brings us to this node. So we know because this node exists, that already means there is at least one suffix of the text that starts with this string, and that will be enough to know that there is an occurrence. The number of leaves is the number of occurrences, and the indices in the leaves is the starting indices of all the occurrences. That's why these are the correct answers. But let's go through this in a little slower pace again. So the first application of suffix trees is the text indexing problem that we started with. And this is the simple equivalence that I implicitly already used. P occurs in T if P is a prefix of a suffix in T. And just maybe because this it might sound more complicated than it really is. Suppose there's occurrence of P and T, so these are all matches. Well, then, of course, you can take this suffix, if there's a position I, you can take this suffix of T, and then P is just a prefix of that suffix, so it starts together with this, and it's an initial substring of this green part. Okay, so P is a prefix of a suffix of T. But there's more to say about this. We have all our suffixes in the suffix tree, so all we have to do is follow paths and see what happens. So no. Now let's do it like this. Here's an algorithm that checks exactly what the occurrences are, and this is the algorithm I briefly sketched on the example, but spelled out in more detail, because there are a couple of different cases in the general case. What we do is we try to follow a path from the root down the tree by following the letters of P. Now, in the case of Anna, we went down here, and then we were in the case that we run out of pattern. We're somewhere in the tree, and our pattern is finished. And that meant that we reach some internal node, or we stop inside the middle of an edge. For Anna, it was in an internal node. And if we say look for BA, we would be stopping in the middle of this edge, right? We run out of pattern and we're still in the middle of one edge. Both cases are essentially the same. They just mean that P occurs at all the leaves in the subtree that are below the point where we stopped. So if we read A and A, Let's do this example here again. That means everything in the subtree here, all leaves in there are occurrences of the pattern, in particular at 3 and 1, as you've seen in the example. And similarly, if you look for BA, you would just get to here, but then everything in the subtree again would be an occurrence of BA. That's probably the easy and intuitive case that we can run into when we're looking for a pattern in the suffix tree. There are two other cases though. One is that we cannot continue. We are stuck in some sense. And what that means is we're at an internal node and there's no edge with the next character that we would like to read, or we're inside an edge and then the next character doesn't match. So two examples for the two cases could be if we look for NB, that's dotted. If we look for NB, we read N and then we cannot continue with the B. Then we fall out of the tree in a sense. Or we are inside an edge. That can happen if we look for BAA. We start reading like here, like for ban, but then the next character is not an N. So we're again falling out of the tree, and that means P does not occur in the text. That's the other case. If you get stuck in whatever way, you fall out of the tree, then the pattern does not occur. There's the last subtle case, which is we run out of tree. We have more pattern, but we reach the end of the tree. We reach the leaf. In general, this can happen, but it doesn't happen in our case with the $sign. If we assume that the pattern cannot contain the $sign, we cannot run out of tree because we would have a mismatch with the dollar at this point. So the only option how this could happen is if you somehow scan past the dollar, but if that doesn't occur in the pattern, it cannot happen. So this case is not really relevant for the text indexing problem. But in general, it can happen if you're using tries for more general problems. So it's that's why I listed it here. But for the text indexing problem and the way we use suffix trees at the moment, this is not an issue. As a final remark is, how long does this take? If we reach this internal node, we can either immediately declare there is a first occurrence. Remember, this is every such node stores a pointer to the leftmost leaf. So we can jump to the leftmost leaf and get its index, and that is a position in the text where the pattern occurs. If we fall out of the tree, then there's no such pointer and there's nothing to return. We just return no match. Both is possible in time linear in the size of the pattern. And I want to stress how amazing this is one more time. You're building a web search engine that stores the entire web, but the time to search for a phrase, I don't know, you search for banana, because it's all banana in this unit. It only takes time proportional to the length of this string banana. It doesn't matter at all how big the data set is. It can be the entire World Wide Web. And that's quite remarkable. It's innocent to state. It's just depending on the pattern, but it's really an amazing result. And suffix trees allow you to get this once you've built your suffix tree for the entire internet. That's only one application of suffix trees. We've already seen a second problem, namely, well, this is almost the same. That's the longest repeated substring. So here we're given a single string, t, and we are interested in finding a string that occurs at two different positions. It starts at I and it also starts at j. So again, you know my favorite pictures. we want the one occurrence at I and one occurrence at j. In principle, we don't object to the fact that these two occurrences can overlap. So I and j could be so that the two occurrences overlap. That's not principally unthinkable. It would mean that the pattern has a certain periodicity. Think back to Unit 5. But that's not the main point for this application here. Again, the question seems to be how to do this efficiently. It seems like you have to check all the substrings in the text. But it turns out suffix trees can do this for you. And let me make this remark, and then I'll show you the example. Whenever you have a repeated substring, anything like this, so again, because that was erased, some position where the same pattern occurs at one position, I, and at another position, j. That means there's two suffixes in the suffix tree, one that starts at I, the entire thing here, and one that starts at j. And they both start with the same shared substring. Now that means they both lead to a certain point in the suffix tree, and then branch off in a different, potentially branch off in a different direction. And in this application, we know they branch off in a different direction. Otherwise, we would have a longer substring that is also shared. So we could just go one more character. So for example, here, again, my favorite example, banana ban. A longest common two suffixes are T5 and T7. A-ban and an. And they have the longest common prefix of A. They only share the A, obviously. Then they differ in the second letter. Now, how is that reflected in the tree? If you take the two suffixes, they correspond to these leaves. Then they're passed from the root. They actually go via here and then here. So they split at this point. And this is exactly an internal node that corresponds to the shared common prefix. Okay? It's a single edge and a single letter here, but in principle, it could be a longer example. If you take 3 and 1, then they would share Anna all the way down here, and you would have a longer path to the last common ancestor. Okay, so this is in general true. If you have repeated substrings in a text, that will mean there's shared paths in the suffix tree. And if there are longest such shared substrings, there will be an internal node in the suffix tree corresponding to this longest shared repeated substring. Okay? And that means we can exploit this fact. If you look at the tree a little closer, then indeed the connection can be made more explicit. The longest common prefix between two suffixes is exactly this lowest common ancestor. Okay, sorry, I'm jumping ahead of myself. I'm not talking about these yet. The longest repeated substring is simply the longest common prefix of two suffixes. And I was confused by the abbreviation, but this is just longest common prefix. The connection to what I mentioned is if you have two such suffixes, the one starting at 1, the one starting at 3, their longest common prefix will be this shared part. And it turns out that this is the label of the lowest common ancestor of those two nodes. It's the lowest ancestor in the tree that they have in common. But the point I'm making here is if you're looking for the longest repeated substring in the entire string, that is the longest common prefix of any two suffixes. So how do we find this? And that's this algorithm here. The first step is we compute the string depth of all the nodes in the suffix tree. So what should that mean? let's make that blue. The string depth is simply how many characters did I have to follow to reach a certain node. And we can start with the root that's at 0. We didn't read any characters to get here. If we go down here, we are at 1, 2, 3 for this node. Now that looks like it's just the ordinary depth, but it differs if edges have a whole string as a label. Then we jump right from 0 to 3. Okay, so that's the string depth. That's the string depth of internal nodes in a suffix tree. The second step is we just find any internal node with the maximal string depth. So in our case, that would be either this one or this one. They actually both have string depth 3. And then the label from the root to any of these maximal string depth nodes, that is your longest repeated substring. So we can either take Anna or we can take Ben. Both have 3 letters and both are repeated and maximal, and that's the longest we can find. So these are very easy algorithms. Once you're given the suffix tree, that would be fairly easy to implement. You walk down the tree once, and you can remember what the current string depth is, and then you just advance that when you walk down. And then you do a second traversal, visit all the nodes, and keep track of what's the largest string depth you've ever seen. Very simple to implement once you're given the suffix tree. So you can solve this problem in linear time using the black box that you can also build the suffix tree in linear time. Okay. That was the application of the longest repeated substring. I initially mixed it up with a different problem, the one that I mentioned in the introduction, that of the longest shared substring, the longest common substring. And we would really like to apply the same kind of technique to this one. So obviously these look similar. The longest repeated substring in one string, it feels like it should have to do with this longest common substring of several strings. There's some subtle differences. We do have restrictions that this common substring must lie entirely inside these others, so it's not useful to have to know that there's two occurrences in T1 but none in the others. So it's a bit more restricted, but it's a very similar question. We try to ask for something repeated but in different strings. So maybe we can solve it in roughly the same way. But an obvious approach would be you build the suffix tree for all the texts, one for T1, one for T2, etc. But that doesn't really seem to help. Because what you need is connect the information about different texts. You somehow need a single big tree that can represent all the strings. And this exists. That's called the generalized suffix trees. And these are, again, a little magic device that is often very helpful. And again, it's the definition is very simple, but they have very profound applications then. So let's look at what this is. The key idea is you make one large text out of the different texts, but you don't just concatenate them. You put a dollar symbol between the texts, and it has to be a different end of text marker for each of the texts. So you try to distinguish them all. You just invent new dollars, $1, $2, etc. So you can keep all the different original texts separate, but they are embedded in one big string T now. And then we construct the suffix tree for this big string. And now, if you look at such a, I'll show an example in a second, but even without that, it's clear that because all these dollars are unique and different, whenever you see a $J edge, it has to lead to a leaf. There's no other way. There's no way any other string can share this. Any other suffix can share this. So we essentially have a leaf for every of the text, tj, and every starting position in the text tj, we have one leaf. And that's the generalized suffix trees. We don't take a single text, we take the suffixes of several texts and all put them into a joined suffix tree. And by building this long text, concatenating the text and separating them, we can use a black box construction for a single suffix tree, for a single string suffix tree, to also get the generalized suffix tree without investing extra brain power. So before we get going with this, a little question for you to wake up again. This time I just put it as a tag cloud, so you can put in any string. The question is, what is the longest common substring of these 3 strings that are given here? We'll use this as an example in a second for the generalized suffix tree, and then you will see how we arrive at the same answer. But I first want to see if you know what the problem is. So remember, the longest common substring has to be a substring of all 3 strings. You have to find a single string that occurs in all of those 3. And then among all of those, you want to find the longest one. You will see that even for this very small instance, that just these 3 strings, and they're not even very long, it's not completely obvious on first sight what is the longest repeated substring. But I'm sure you will figure it out. I see 10 answers. Again, if you feel like you have no idea what I'm talking about, a valid answer is I'm lost or don't know. And otherwise, try to find the longest common substring of BCA, BCAC, AA, BCA, and BCAA. Great words to pronounce. We have 14 votes. I'd love to see a few more. Can we get our usual 25? And in case you have no idea, you just submit anything random. I like the FFF. Someone sent a number. Don't send the length. Send the actual string. Maybe you can still edit this. Come on, guys. 25. I want to see 25. We got 26 in the previous, 31 on the first. There must be some people hidden. $20 is good. 25 would be better. Yeah. Results are coming in. That's great. 2 more. 1 more. Tension is rising. There we go. Awesome. Okay, we have lots of votes for BCA, and that is correct. For all the other examples, I think AA is... No, all the other examples are not common substrings. They're not substrings of all the 3. Yeah. So BCA is the correct answer. And let's see. How would you prove this? Well, you can see the occurrence here in all the 3 strings. And well, it actually occurs twice in the first one, so you can take any of the 2 occurrences. And there's no longer such string. It's easy in this example to see, well, the only longer option would be BCAA, because that's the entire last string. And there's no double A in the first one, so that won't work with all 3 strings. So how can we do this now systematically and using suffix trees? Here's an algorithm. And again, this might be a bit small. So of course, we start with computing the generalized suffix tree. There will be an example on the next slide, but I want to give you the algorithm first. You compute the generalized suffix tree for all the strings. That is the core information is in the tree, but you have to add a little extra information to find a substring that is common to all substrings. Maybe let me go back very briefly to this one. What we did here is we asked for the longest repeated substring. We asked for any string that occurs at least twice. For that, because we use a compact trie, any internal node of these little dots here, any internal node will have at least 2 different leaves in its subtree, 2 different leaf descendants. And so any internal node was fine for getting a repeated substring. Okay. Now, in this new problem of the longest common substring, this is not enough. We want that this substring occurs in all of the strings. So we have to work a little extra for that. And what we do is we traverse the suffix tree, and we store at each node the subset of all the strings that have a leaf below it. So each node stores the set of numbers j so that there is a leaf j comma I, so that's not an I. Started the suffix that starts at I in position in string j. In the subtree. Okay, that's the idea. Once I have this computed, and once I have the string depths, I know that I only have to find the deepest, the node that has that stores the set of all strings, and among those, the one with the largest string depth. Okay. Remember, every repeated string gives rise to an internal node, but we want an internal node where there's a continuation in all of the strings. So we try to find one, the deepest node that is labeled with all of the strings, and deepest in terms of the string depth. Okay. If you go through this algorithm, computing the suffix tree takes time proportional to the length of all the texts, because that's the text we compute, and that we compute the single suffix tree on. And both of the other things are linear in the size of the suffix tree, and the suffix tree is linear in the number of characters. So again, here's this quote from before. We found this linear time algorithm now for this problem, and that's proving a famous computer scientist wrong. So here's an example that might make this algorithm a little clearer. It's from the same 3 strings that I asked you about, and you can see, so there are different leaves. I labeled them here with the actual string instead of just the pair ji. But you see that the $sign at the end tells you what string it is from, right? So if it says here, I don't know, let's pick $2, that must be this A as opposed to this A, because it's followed by $2, that indicates it's from the second string. Okay, and similarly for all the others. And what you see in green, these are these subsets. So maybe make the entire thing green. The nodes store these subsets in green. That is simply what indices of dollars do I have below me. This node has only $2 and $1, so it stores 1, 2. This node has $2, $3, and $1, so it stores all 3. And so on for all the others. And you can compute this bottom up. If you're a node that only has leaves, you just walk through all the leaves and check what dollars are there, and you take note of the result. If you're an internal node with several children, then you just take the union of all of these. You have $1, $2, $3, that would already be enough, but you take the union also with 2, 3, and 1, 2. I hope the example is enough to help you see what this algorithm is doing. By computing these green sets, the collection of all dollar indices in the leaves below this node. The second step is computing the string depths again, and that's exactly as we've seen it before. So let me just add these here, and that's 2, that's a 4, and here another 2. And now we try to find the deepest node that has all 3 letters, all 3 strings in its label. So we can only take this node, this node, this node, this node, this node, and clearly this one is the one that's deepest, and it's labeled by BCA, our longest common substring.